Every second, trillions of tiny particles of light strike our world. Most pass unnoticed. But over a century ago, one mysterious experiment revealed that light behaves in a way no one expected. That discovery shattered classical physics and helped launch the age of quantum mechanics. For centuries, scientists believed light was purely a wave, a gentle ripple spreading through space. Waves interfere, diffract, and bend, explaining rainbows, shimmering colors, and soft edges of shadows. Then came James Clerk Maxwell. His equations united electricity and magnetism into a single elegant theory of light. Classical physics predicted that brighter light carried more energy and that time could charge matter with that energy. Confident and consistent, the wave picture seemed complete. Wavelength and frequency mapped the colors of the spectrum: red, green, blue, each a graceful oscillation. If light is only a wave, intensity, its brightness, should control how much energy it can deliver. And yet, a quiet experiment would soon refuse to obey those expectations. In a quiet laboratory, physicists shone light onto a clean metal surface sealed inside a vacuum tube. Wire leads carried a measurable current. Meters tracked the electrons ejected from the metal. When light shines on certain metals, electrons are released. Inside the metal, electrons move freely, bound only enough to keep them from escaping into space. Light arrives, energy in discrete packets or continuous waves. The experiment held the answer. Electrons leap from the surface and race into the tube, forming a current. With the light on, the meter moves. With it off, the signal vanishes. Simple, repeatable, and soon profoundly disturbing to classical theory. Observation 1. Brighter light releases more electrons, but not more energetic ones. Classical waves predict more energy with more brightness, yet the electron energies do not rise. Observation 2. Blue and ultraviolet light eject electrons, while red light often does not. Frequency, not brightness, seems to unlock the surface. Observation 3. Electrons are emitted instantly, with virtually no delay. A wave delivering energy gradually should need time to charge an electron enough to escape. So why does frequency matter more than brightness? If light is only a wave, why does frequency matter more than brightness? In 1905, a young patent clerk named Albert Einstein proposed a bold idea. Light, he argued, comes in tiny packets of energy called photons. He wrote it simply: E equals to hf. E is energy, h is Planck's constant, and f is the light's frequency. Low-frequency photons carry little energy. High-frequency photons carry much more. Each photon gives its entire energy to a single electron, instantly. If E equals hf, frequency governs the punch each photon delivers. Every metal holds its electrons with a certain binding energy called the work function. Think of it as a hill. An electron must climb to escape to the outside world. If a photon's energy exceeds that hill, the electron can leave. If not, nothing happens, no matter how bright the light is. Above the threshold, the extra energy becomes the electron's kinetic energy. Like pushing a ball over a ridge, once past the top, it speeds down. Higher frequency makes each electron more energetic. Higher brightness makes more electrons, if frequency is high enough. Scientists varied the light's intensity and watched the current grow. More brightness created more emitted electrons. Then they changed the frequency, and the electron energies jumped. By applying a reverse voltage, they measured the maximum kinetic energy of the electrons. Energy rose linearly with frequency, not brightness. The slope matched Planck's constant. Emission was essentially instantaneous. For explaining the photoelectric effect, Einstein was awarded the Nobel Prize in Physics. A simple experiment had revealed a quantum truth. The photoelectric effect became powerful evidence that light is both wave and particle. Wave-particle duality reshaped physics at its foundation. From atoms to accelerators, quantum ideas guided a new era of discovery. Today, engineered quantum systems push the boundaries of computation and sensing. Light behaves as a continuous wave in some experiments and as discrete photons in others. A revolution born from careful measurement and daring ideas. In solar cells, photons free electrons and create currents that power homes and cities. Digital cameras convert incoming photons into electrical signals, one pixel at a time. Light sensors open doors and guide machines with invisible beams. Smoke detectors spot scattered light when particles drift through a beam. Fiber networks send encoded photons across continents at light speed. Detectors turn high-energy photons into images that reveal the hidden interior. In space, exquisitely sensitive sensors count single photons from distant galaxies. Even navigation depends on carefully measured light. Across technologies, the same principle repeats: photons in, electrons out. Electronics measure and amplify these currents, turning light into data. Every smartphone camera, every solar panel, and countless instruments rely on principles revealed by the photoelectric effect. From clean rooms to cryostats, engineers refine the quantum control of light and matter. One unexpected experiment transformed science and our everyday lives. The photoelectric effect did more than explain light. It opened the door to the quantum universe, forever changing our understanding of reality. Sometimes, the smallest particles illuminate the biggest truths.